Let's go. We are live, day 46 of the challenge. And thank you for 74 subscribers. I think we are blowing up now. We are blowing up. I'm happy. Okay, we are doing great now. So yes, we'll go live through this one too. We'll spice it up. Let's just do it. Now, equilibrium. That's the chapter we're gonna do. You can see from the taskbar. The first chemistry chapter. Equilibrium is basically something which is very important to know. Equilibrium can be classified into two: static equilibrium and kinetic equilibrium. Yes, there are two types: static equilibrium and the kinetic equilibrium. Now, static equilibrium is basically very important to understand here. Why should we basically understand this? Why is it very important? We'll go through each and every one of them, but first of all, we'll understand what exactly the static equilibrium is. Here in static equilibrium, no reaction exactly takes place. So yes, there is not much of a probability of saying that yes, there is a reaction taking place. The reactants or concentration will be the same. Product's concentration won't be there. So therefore, since there is no rate of reaction or no net rate of reaction, then we can say yeah, the equilibrium is there. But this kind of equilibrium is static equilibrium because nothing much is going on here. If there's some kind of action going on, but then the net rate of the reaction is still zero, then we'll call this as kinetic equilibrium. In this, the reaction here takes place, but the reaction that will be taking place will be a reversible reaction. Okay, so it's going to be a reversible reaction, and in this one we will understand how is it reversible. We'll understand through the whole mechanics. Okay, so we're going to do it. Now, reversible reaction is very important to understand, going through each and every one of them, getting the idea of yes, this is happening and this is not happening. So first of all, let's say, oh yeah, this is known as dynamic, by the way, you know that. So kinetic, but then it's dynamic because there is cause too. Equilibrium should also have the cause. That's why we're including dynamic equilibrium. This reaction will be reversible, and therefore they will be denoted by a reversible sign, where the reactant gets converted into products, and products being converted into reactants. Yep, here we have it. Okay. Now, reversible reactions are very important to understand. They are very important. Like, we need to get an idea based on what we're gonna do next. So let's just mention the reversible reaction. Alright, so reversible reactions. Well, first of all, let's go through the reaction. The dynamic equilibrium. Okay, so there are three types of dynamic equilibrium. The first one is known as physical equilibrium, which we are going to study. Second one is known as chemical equilibrium, which we are going to understand. And the third kind of equilibrium. What is the third kind of equilibrium? The third kind of equilibrium is basically known as the ionic equilibrium. Alright, let's go to this side just to make it much better in the angle of perspective. So yeah, third angle of here and bam. That's how we are actually acing our critical streams. Okay. Let's go. Alright. Anyways, I don't know why I go to deep tip. Never mind, let's not say that. So yes, oh hi there. Okay, so there is a deep thinking. You need to have an idea based on that. And then we have equilibrium that is going on here. What is that equilibrium? What exactly is going on into that equilibrium? Let's understand one by one about that equilibrium. So EQM is the representation of the equilibrium. Equilibrium is also given in other terms. Okay, so we're gonna understand them each by each, one by one, and easy, nicely. So equilibrium is very important to note. It's very important to guess it out, and many ways. Okay, very ways. All right, that was very weird. So now let's start off. Now, equilibrium, dynamic, the concentration of the reactants. Yeah, they can get converted into concentration of products. But again, concentration of products gets converted into concentration of reactants, meaning that the concentration of reactants and products is remaining constant such that the rate of forward reaction is equal to the rate of backward reaction. So when there are many of them, and we're gonna go each of them. And let's first of all learn physical equilibrium. So we're gonna understand the physical equilibrium. Physical equilibrium. What is going to be the basic of physical equilibrium? What exactly are we understanding in physical equilibrium? In order to go through that physical equilibrium, let's just talk about water. Water. I don't have water right now, but once we take the solid of H2O, then get converted into a liquid form of water. That is, of course, the H2O, that is ice being converted into water, and that is the solidifying part. Ice being converted into water, solid into liquid. Nice. We got it. Okay, we are getting it nicely and correctly, and it's a very great method. Wait a minute, guys. I've got to know what you think. Just show that. Oh, yo. Let's go. You're gonna understand this part, so wait a minute. Okay. Let's switch this on. Oh shoot, that was gonna reveal almost everything, but did not reveal it. Oh yeah. Litty, yo. Litty, yo. Let's go. Okay. I'm going to live. Wait a minute. Here was Fanite, huh? It's Fanite. Yo. Hey, bro. I'm studying equilibrium, chemistry. H2O solid being converted into H2O liquid. Now H2O solid. Wait a minute. Alright, let's go. Let's go. This is working nicely and great. But the problem is meat or J. Neat, okay. You know what's the idea. You know it. Physical process equilibrium. Solid to liquid. Suppose I do not have ice. I need to get ice. I don't have it. If I have it, then I would have got water. Okay, I'm so stupid. Anyways, yo, have some self-respect. I'm having some self-respect. I know what's going on in that camp, okay? Yep, okay, never mind. Svanite. Yes, I will. You know what? You know the idea. You know the answer. Okay, I like maths. Maths better? Yeah, it's fine. I like maths. I do not go against that opinion, my boy. I like it. Maths is great. If you want, you can say maths is better than physics, chemistry, biology. I'll still be satisfied. That's fine. I'm not gonna be angry, man. I don't like going, back and forth. Oh, from the word of back and forth, we understand backward reactions and forward reactions, which are basically a part of chemical equilibrium. Now, suppose, let's understand this through an example, okay? Suppose there is a person who does not revise at all. He doesn't revise anything. He is just like, studying continuously, but he ain't revising. He knows the new topics, but he forgets the old topics. Like, bro, if you're studying the new topics, it's fine, but if you don't revise the old topics, you're just forgetting them, meaning that he's maintaining equilibrium. Equilibrium is just one of the perfect examples that takes place in our life. What does the series 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 converge to? Alright, I gotta use that to solve it. Alright, just wait a minute. That is very interesting now, huh? R as 1 by 2, A as this one, converge to. Alright, okay. Okay, wait, is this an infinite series? Just tell me. Just tell me if this is an infinite series. Because I feel like, yes, it is an infinite series. Is this an infinite series? Yo, I'm accidentally using mathematics in chemistry. What the hell? Yo, I'm studying chemistry and you gave me mathematics. What? Oh, sure. You know what, Sven, I will show you something which you really hate. Just wait for a minute, okay? I'm gonna show you something which you really hate. Okay, just wait, Sven. Ah, this is gonna be very utterly weird. Yes. But yeah, remember that I'm your fan. Yes, okay. By the way, just tell me if this is an infinite series, because I feel like, yes, this is an infinite series. If I get this as A by 1 minus R, okay. Okay. This is the one. 2 minus. Wait, okay, 1 by 2, okay. Alright, we have 2 viewers watching. Oh, wait a minute. Let me just check my live, okay? Let me just check my live. Is it working nicely? What is going on here, dude? Yo, what the hell, man? Okay, I think it's an infinite series. That's what I know. Just wait for a minute and I'll give you the answer, okay? I'm still solving it. It's very easy, I know, that's for sure. That is GP. I know that. I know that's GP. And yeah, you Svana, look at this, man. You got something very a kind of sub begging which you really hate. Just wait a minute if I just to check, okay? Oh my god, bro! Just consumers equilibrium or producers equilibrium? I'll go with no, it's not economics, dude. It's chemistry equilibrium. There are many equilibriums that exist in our life. I'm not talking about that. Wait a minute, let me just check my live, dude. And then I'll give you the answer too, because I still have to solve a bit. But yeah, I'm almost gonna do it. It's an easy question. I know what you're trying to say. Just wait a minute, because I feel like my voice is lagging. Yeah, that's what I'm saying. Just wait. I have to first check my live. I'm still doing it. If you want, you can check it out. Here, still I'm doing, okay. Wait. Just wait a minute. I feel like my cam is lagging. Wait a minute. I have to check my stream again and again and again and again and again and again and again. So yeah. Bro, oh my god, this is so utterly weird. Oh no. Yeah, I know, but I have to check it again and 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 again. A cyclic process. You know what cyclic photophosphorylation? If you don't know, it's fine, because you're a commerce student. That's what I know. Wait a minute. Totality. Yo. I see that. Okay. Wait a minute. Here we go. My live. And we go here. Let's check it. Okay. Let's see. Looks like rotational motion mentioned. GOAT. This message is held for review. What? Yep, okay. Oh yeah, you were saying this, right? Let me calculate it. 1 minute. Wait a minute, it's finite. Wait a minute, it's finite. So since this is an infinite series, I get the answer as 2, okay? Since it is an infinite series. The question I got, you're saying that 1 by 2 plus 1, say 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 dot dot dot. It's an infinite series. So I got the answer as 2, okay? That's what I'm saying. I got the answer as 2, okay? Because you did not give me the point or the nth term, that's why. And please wait a minute, I gotta study chemistry, not mathematics. Even though I like mathematics, doesn't mean that I gotta go through the whole thing, man. W is finite though. W is finite. Goat. Yeah, I like rotational motion. You study moment of inertia, you study angular momentum, you study angular acceleration, angular velocity. Then you study about radius of gyration, many stuff. It's really interesting. It's really good. I like it. It's also very much related to circular motion that you study, uniform circular motion. But there is a difference because in circular motion there is a point object which has its. Okay, what is the locomotion of oxygen? You mean the movement of the oxygen? Bro, entropy, randomness. It could be very high, it could be maximum. But yes, again, I'm not sure whether I've studied that anywhere here, but I feel like I can say there is a high entropy. You know what's entropy? State of randomness or more disorderedness. Yeah, that's what I can say. That's what I know overall. Okay, never mind. Solid gas equilibrium. Can I know in which class are you in? Looking like a class 12 boy who has studied from YouTube. Bro, SHSJ09 has literally got an accurate prediction, but there's one mistake. I'm actually a class 11th boy, a science student. Yes, bro, how did you get to know that I study from YouTube? Oh, shoot. Oh, okay, maybe, yeah. I think because I'm a YouTuber. My bad. My bad. Oh man, I'm so stupid sometimes, I don't know why. Bro, have some self respect. Oh yeah, my bad. My bad's finite. Oh shoot, I'm overreacting. Solid to gas equilibrium. Let's have camphor balls. Okay, camphor balls. Let's say this is rubber, but then this is not camphor. Now the camphor, when I keep it in its place, suppose here. Also, see, I'ma do some random BS. What is BS actually? What do you mean by BS? Yeah, and bye, bro. If you wanna go, I have no idea what's BS. Is it Brawl Stars or something? Business studies could be. Oh yeah, man. I usually get confused with business studies and Brawl Stars. Oh yeah. I usually get confused. Now, solid gas equilibrium. Camphor gets converted in the form of gaseous state, meaning that camphor of solid state, reversible reaction. I'm 23 years old. I can tell you your face, language, and energy because I have been through all phases and seen many. Oh, okay, sir. I see you, sir. Respect to you, man. Respect to you. I give you, sir. Thank you very much. Thank you. Yes. Looks like we are doing great. Okay, we're doing great here. And also this is kind of very weird because you're saying that I have studied through YouTube, and you said you have gone through many phases. So did you study from PW? Physics wala? I'm not sure. Could be. Could be. I don't know. You look like you're gonna say something which is basically like studying through YouTube. Yep. Poink. Obviously. Alak Pandey. Bro has studied from Alak Pandey. That's what I can say for sure now. Is it? Is it? I have no idea. I'm just saying it. I'm just saying it. Bro, even though you're saying obviously, I have no idea. I'm just guessing out because that's the highest way I can get the prediction correct. So yes, but still I can understand you, sir. I salute you. You're one of those OG people I know. Nice. Equilibrium involving dissolution now. Equilibrium involving dissolution, that is dissolving, getting converted to this. Shoo you. Are you from India? English is crazy, man. Yeah. Yeah, I know. I just want to have my targeted audience all around the world, not just Indian people. But yes, I'm actually from India, but again, I live in Gulf. I do not live in India. I'm not in India actually. I'm an Indian, but I live in a Gulf country. So yes, that's one thing you should know actually. In equilibrium involving the dissolution that a solid gets converted into liquid, and that is here to here, right? Yep. So wait a minute. Solid and liquid. Oh, sugar solid. Then it gets converted into sugar aqueous solution. So what I can say here is the sugar. Oh wait, I forgot there is another live going on. Oh shit. Oh okay, here we go. And my cam is stuck. Nice. Sugar solid getting converted into a solution. Kind of interesting to know that. Aqueous solution. Now, okay, next thing here is gases in liquid. Gases in a liquid. Alright, we get CO2 and getting converted into what? Gaseous to a liquid state. What? Okay, this is interesting. CO2 gaseous to CO2 in liquid state. Now, let's understand this one by one. We have gaseous state of CO2 and the liquid state of CO2. Yes, we really do have one. Oh, let's go. I have a respect for those people who are OG, man. That's great. That is great. That is great. Okay. Let's go. Okay. It says that two watching is the thing that says it. Oh my god, this is very interesting. You wanna let me speak in English? Indian English? Alright. Look up Indian English. Hello sir, what to do? This is me. Totality higher. Okay. I'm Indian, but also I live in Gulf. Just kidding. I can speak normal English. I'm just kidding, boy. Bro skipped. Oh sure, he skipped. Okay. Robert W. Let's see if he is live. I don't think so. He's most probably live, but he might watch my going on. Oh, bro, what is going on here? Click. Clink, clink, clank, clink, 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 clank, clank. Yep. Yep. Let's go. You're doing it. 74. My laptop cam is stuck, dude. What, bro? What is going on? My laptop cam is stuck. Yo. I'm sick of this. Let's just record. Let's repair it. DVD. Oh, yo, hi there. How are you doing? This is me going through this. Then, BAM! No, what? No, dude. Got stuck. Let's go. There are two lives going now, huh? Now, CO2 gaseous converted into CO2 liquid. That is what is going on here. So CO2 gaseous to converting into CO2 liquid. That is interesting, by the way. So solubility of the gas increases by the pressure of gas, and that is known as Henry's law. Solubility of gas increases the pressure of gas, making the concentration a bit more, actually, not gonna lie. If this gas is soluble, if it is like directly getting into this questions. Yep. Soda water bottle is sealed under pressure. Why is it so? See, if this is sealed under the pressure, it increases the solubility of the water having carbon dioxide, meaning that the carbonated water will be there. Yes, carbonated water is going to be present, and therefore we have the carbonated water. Okay, that is, let's say you want Coca-Cola, Pepsi, or that was I'm not gonna drink those, but yes, Coca-Cola, Pepsi, those have, there will be pressure inside them. Now this pressure inside them, you can see, is actually very interesting to note it down. The pressure is max, where since the pressure being max, the solubility of the gas is also increased because it's following Henry's law. So we can say that if the solubility of gas is increased, our pressure of gas will be increased, showing the proportionality sign, and therefore we get the idea of, yes, that's how it's happening and that's how it's going. Yep, that's how we get an idea based on that. Now, all right, all right, all right. Now, what is the next one? Okay. So P is directly proportional to the partial pressure, is directly proportional, what we can say is to the mole fraction of the gas. Mole fraction, that is chi. Chi. Okay, then that's not the chi you're talking about. No, it's X actually, what's known as chi. That is the mole fraction. Okay, this is very boring content. I swear I make very boring content, but trust me, I can do it better. Yeah. Chi. And then we got partial pressure. Now, what is partial pressure? The pressure of that specific substance is known as partial pressure. Yes, the specific pressure, or the specific substance pressure is known as partial pressure, and therefore we get the partial pressure of a gas being directly proportional to mole fraction of a gas. That's how it is increasing actually. Now let's basically understand another fact. Oh yeah, I forgot that there's life going on here too. Now, soda water when left in air turns flat. Why does it? So why is it basically turning flat? Like, what is going on? We need to understand that too. So first of all, what we're going to do is that we need to write the Henry's law. So let's write Henry's law. Let's practice it. So the law states that um, the partial pressure of a substance pressure of a substance is directly proportional to is directly proportional to the mole fraction of a substance. Actually, it's a gaseous substance, by the way. Gaseous substance. Yes, mole fraction of the gaseous substance. Yep. Fraction of gas, or yeah, in solution. In vapor phase. Of the gas in vapor phase. That's very weird to say gas being vapor phase. Huh? Okay. You know what? Let's just write this again. It's fine. You can do it. Oh man, I had to end the stream now. Like literally, I should do that. Like, dude, what the hell is this? Oh, that's messed up. Oh, that is messed up. Oh. Oh, my charge is getting so low. I have no. But it's fine. I will be still streaming through this. Yep. Okay. Bro, like, why am I doing this so bad? Like, what is going on? Let's check this out. Let's just check it out. Got this DV20 camera, and here we go. Like, bro, what's going on? I still did not understand. What? Alright, let's go. Finally, it's working. Yep, here we go. Here we go! The law states that the partial pressure of a substance, the partial pressure of a substance is directly proportional hmm, to the mole fraction, okay, you know what, of a gas in vapor phase. That's what it says. To the mole fraction of gas in solution. Of gas in solution. Solution. Alright. Oh, yep. Yep. Equilibrium in a chemical process now. So soda water can is sealed under pressure of gas when it's Yarkas. I don't know. Anyways, let's go. We're gonna understand this. So first of all, we got the partial pressure of a gas being directly proportional to mole fraction of a gas in the solution. Yes, we got this. All right. Let's go. Equilibrium in a chemical substance. I think my phone is gonna go dead soon. Equilibrium in a chemical substance. That's the mean. Pressure or solubility. Okay, here we go. The chemical process. Solubility of gas in liquid increases with increase in temperature, though. So solubility of a gas increases or decreases when temperature how though with temperature increase. Alright, we got it. Okay, equilibrium in a chemical process. Yep, guys, looks like it's coming to an end, but don't worry, I'm still gonna continue. Equilibrium in a chemical process. Okay, we aren't giving up. Let's say that there's a chemical substance A reacting with chemical substance B to give a chemical substance C and D. But this is also another thing, that this chemical substance C and D again can react from a chemical A and B. So in the beginning, concentration of A and B are maximum, and hence rate of forward reaction will be max. So yeah, that's the one idea. Then okay. Oh shoot. Oh shit. Ah, that hurts. Ah, that hurts. Oh shoot, that hurts. Yo, that hurts. Oh shoot. I'm never gonna touch that. Yo, veins are veins. It's fine. Can block that, but then, dude, that kind of hurts. Arteries. Yep. Wait a minute. Our arteries. Location of arteries in brain. Sorry, in elbow. Yes, elbow joint. Okay, that's great. Oh shoot, that hurts so bad. Like, dude. Cubital fossa. Oh. Let's not touch that. Right. Okay, let's go. We can do it. A plus B reacts with C plus D. Loading this. Okay, rate of backward reaction increases due to increase in concentration of C and D. When the rate of forward reaction and backward reaction equal, the system attains equilibrium. That is the state of an equilibrium. Oh, the graphs of equilibrium. How can we forget that? So, we need to have an idea based on this. So, what is the exact graph of an equilibrium? That there is a time where the reactance concentration and the concentration of this product gets combined together, and this gives you the equilibrium concentration. This is throughout the time, and this is your reactant concentration, and this is your product concentration. Product concentration, giving us a basic idea, or we can say rate. It's not a matter of saying that time or rate. Then there is another graph where you can actually justify that concentration is equal. Suppose we can say that reactants are being here and product here, that is A plus B. Forward reactions require C plus D. Reactant here, and yes, reactants coming here, and then there is products here, that's you can say, and then overall this is the rate. Okay, equilibrium equation. Okay, now this is very important. We're coming something to very important, that is known as law of mass action. Then how long is this chemical equilibrium? We're gonna check this out first. Okay, yes, it's a bit time taking, but don't worry, we can still do it. Still a bit time taking, but yep, we can do it. Yes. Okay, many numericals. Oh wait, okay, we reached a point where it gets ionic equilibrium. Where is it? Ionic equilibrium. What? Yep, okay. Alright, looks like I will be charging this phone, so I will be going live through another device after dinner, but I will be still live here, so don't worry. Okay, so yep, bye for now. For this stream I will still continue. What is going on here? What is this? Mirror side sibling. What is, okay, what is skeleton there? Still do not understand. Okay, I did not turn into a skeleton. Did I remove this? And did I turn into a skeleton? kaleidoscope. Here we go. Yep. Man, I do not like this because it's very trippy. It is very, very trippy. Hey, Weaver. That is very weird. That's very weird. This should be a thumbnail. This should be a thumbnail. Big head, yep. Still remember this. This one is really good. I got actually that problem through this one. But let's not use that. Yep, no effects. Yep. Looks like I'll be ending the stream to this one, and then I'm gonna continue to this device. Okay. Right. Alright, not bad. Today it was fine. This has been private. We're gonna switch that up.
These are my top 3, you guys. I love these 3 so much. Oh my god, I feel like I have to keep flying.
Let's make this public. Save. Yep. Now let's continue. Equilibrium equation. Law of state law of mass action. Law of mass action. All right. Oh, that was gonna drain its battery. Not look at the battery at all. And here we go. Let's go. Okay, this is working. Alright. Let's reload this. I don't think he is live. Maybe not. Yep, he is not live. I mean, it's still fine. Not worried because he will take his time. He said that he has something going on. So yep. The rate of chemical. Okay, what is mass action? By the way, active, that's known as active mass, which is also known as concentration in today's term, or pressure in gaseous methods. So yeah, that is one thing you should note down. Okay, the rate of chemical reaction is directly proportional to, I don't know whether I'll get time for numericals, but I'm trying my best. It is directly proportional do the okay. Robber. Robber with robber. Ha ha ha. Oh, yes, yes, yes. I'm doing it. We're doing it, guys.
Okay, my favorites are the
Okay.
this one. Oh, to cocoa.
Nice, we did it. The rate of chemical reaction is directly proportional to the products of active masses of the reactants. Rate of chemical reaction. You know what? I have something crazy to do. You know what? Let's do it. Just wait for a minute. Come back. This is gonna be much crazy. Sure.
By the way, my least favorite is this one. Wait, look, first of all, she's too Christmas card. Second of all, she could have gotten a cuter Christmas card. It's cute that the fact that she's a little Christmas tree, but she could have gotten a cuter Christmas outfit. And I don't really like the color palette, but she's really cute. I love her face, but I don't really like the color palette. Least favorite. So cute. I'm waiting for that blue one. It's on the two, right? Yeah, it's on the two. She's so cute.
Mirchi pani. Yo, what the hell? Wait a minute. What? Day 46.
Your face is cute, but I don't like the costume.
Okay,
But she's so cute.
what?
This one's nice.
What is she talking about?
Okay, I like.
I'm not getting any idea. Oh, wait a minute. I noticed something. This can be.
I know this is a Christmas set. That's why they are supposed to be Christmas colors.
Bro, what's going on?
Only two are of them are. Oh my gosh, she's my face.
Yo, what?
So cute. Oh no.
What's going on? I cannot understand anything. Cannot change them. What?
Oh my god, what the
Also, my stream got stuck.
Blush blindness. She got blush blindness.
Like, dude, oh my god, I should have done that.
She's just a little.
It says one weave, it's fine.
Snowflake? But you can't say that directly. It's supposed to be snowflakes when you return.
Oh, sure, what is this?
Um,
Bro, what is this? Yo, what? Also, let's check YouTube Studio now. Got an idea?
so cute. Okay, I'm keeping on
No.
and you guys I feel like nobody likes this because it's feel bad. Like I feel like this is the worst. It's okay, you deserve it.
Okay, what?
These are my babies. These are my puppies. This one's not.
The rate of chemical reaction is directly proportional to the product of active masses of the reactants. Yes, that's done. That being said, A plus B. Rate of forward reaction is equal to, directly proportional to concentration A, concentration B. What? I did not get any idea. Rate of backward reaction. C plus D. No, what is this, bro? My cam. Oh, shoot. Check that. I'll take this. Yep. Take that. Put that in, and here we go. Let's change that up. Now it's supposed to be changing. Yep. Here we go. F is equal to KCAB.
उसका नाम स्ट्रेप्सिल्स करके बोलता है
लिप्स के साथ पे
हाँ वो गला ही
B KCCD. Okay, never mind. Uh, 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 uh. At equilibrium, Kf, concentration of A multiplied by concentration B, Kb, concentration of C multiplied by concentration of D, Kf by Kb is equal to therefore Kf by Kb is equal to C and D divided by A and here B. Therefore, we get concentration Kc is equal to C into D active mass A into B. Let's go. Let's go. Okay, that was very zesty. I don't want to do that. My bad. Law of chemical equilibrium. Yay. Let's go, guys. We're going to do law of chemical equilibrium. Law of chemical equilibrium. Now, what is law? Okay, wait. First law we studied was equilibrium. What is the first law we have studied? The first law we studied was law of Henry's law. Not law of Henry, my bad, Henry's law. The partial pressure of a gas in vapor state is directly proportional to the mole fraction of a gas in solution. That's the first one. Second one, okay, I don't wanted to do that, my bad. The second one, that is law of active mass. So the concentration, the rate of the reaction is directly proportional to the product of atomic masses. And the third law, that is the law of chemical equilibrium, which we are gonna do now. First of all, we can note this down. This formula, Kc is equal to C into D. Their concentrations, by the way, A into D. They are represented by their square brackets. Yeah, hey boy, let's go. Now, their stoichiometry is also given. So their stoichiometry is to their powers. So, yeah, we can write that down. We're doing great. Here we go. This is day 46. Day. Boy, At a given temperature, the product of concentration of the products raised to the respective stoichiometry or coefficient in a balanced chemical reaction equation divided to the product of the concentration of reactants raised to the individual stoichiometric coefficient as a constant value. Very big law, but it describes the specific formula, so it's not at all that hard, actually, not gonna lie. So yep, we're gonna go through each of them. Okay, we're gonna understand them, we're gonna do it. Alright. Next is homogeneous, and what else next? Kp and Kc. Oh yeah, this could be important, we have to go through this. Then we have numericals, which we'll be doing later, not now. Then heterogeneous equilibrium, we'll be doing that later too. Wait, are we hitting ionic equilibria that fast? Application of equilibrium constant, that is also important. We're gonna study that too. And then we finally hit, bro, how many numericals are there? There are many of them, plenty of them. We're gonna give some time for all of these. Yes, factors affecting equilibria. Oh sure, there are many of these. I don't know whether we can complete it. Wait, this is Lee Chatellier's is this? Yeah, could be. Oh yeah, it is that one. Oh yep, that's it. So yeah, without wasting time, let's move on. Let's write the law of chemical equilibrium. At a constant temperature,
Okay, sorry. If I'm gonna quite honest, I'm not most favorite like, don't get me wrong, I love it so dang much. But the thing is that I just isn't like the fact that they're involved is cute, but like I wish that the opening was just a little bit more big. But they are really cute. I know they're really cute. So yeah. Okay. But okay. Let me show you all the ones that I like. Okay. Hello. Okay. And my favorite, like so far, like my most favorite one is this one. The full sensor. Like I love the gold.
Okay, I was thinking about my bad.
Gold pen inside is just so cute. I really like this one. This one. This one. Actually, I like all of them, but this one's my. I also really like this one, this one, this one. Yeah, but they all are really pretty. I love
Oh, yep.
really love. Okay.
Let's open this. Let's check this live.
She is so pretty. Wait, this is the one that I want, right? She is so pretty. Oh my god. Oh wow. No, I want. Display her like that because she's so pretty. For now, I'm gonna display her like that, okay? She just still look pretty.
Okay. Bro, I'm lagging so bad. Really?
Oh my god. Oh my god, this is so class. I love blue. Blue is so pretty. Blue is such a pretty color. Like if you don't like blue, you're like I'm like you're missing out.
Okay.
You're missing out. Oh my gosh, so pretty. Man, I love the color combination in like the black and the red. Oh my god, this is the one that is the most. This is the most unique one. This is the. She's in front of the box because I mean she deserves to be in front of the box, but she's not in my favorite.
Okay.
I don't really like the eyes that much, but I love everything about her. Like the ball, the
Right.
bird, the.
Stream is going a bit laggy, but it's still fine.
She deserves.
Okay.
Like, but the thing is that I don't like without the piece, she kind of looks like incomplete. So that's why I don't really like this one. So far, my grade series.
The product of concentration of products raised to the respective stoichiometric coefficient divided by
This one is really cute. I definitely like this one.
product of concentration.
Okay, I would even care about the ball. I love the ball. Sorry, not the ball. The ball. I love the ball too because the opening. Oh my gosh.
Okay. Here we go.
Okay, this is not the one that I want. Oh my god.
Individual
My second favorite. Oh my god.
visual stoichiometric
She's so cute. Oh my god. So small. Like, seriously,
coefficients.
why do you do this? Okay, let's start this one. I can see this
Okay.
one now. So, why do you do this?
As a constant
No, I
value.
feel like the artist is open,
Alright, I think this is the law. It's a very big law though.
opening for the most.
So at a given temperature, the product of the concentration of the products raised to their respective stoichiometric coefficient is divided by the product of the concentration of the reactants raised to their individual stoichiometric coefficient such that as a constant value, yeah, raised to their individual stoichiometric coefficients as their constant value, and therefore we get the idea of this one. Yep, here we did. Here we go. Now, homogeneous equilibrium. All the reactants and products have their, same. Okay, homogeneous and heterogeneous equilibrium. Homogeneous equilibrium. All the reactants and product have this are in same phase when they are in the equilibrium state, and the same thing goes in here. That heterogeneous equilibrium. Uh, you know. Okay.
I like the ball though. It's like so shiny.
Nice. Oh yeah, I'm gonna show that Kp and Kc, and then we're gonna show, I guess, the heterogeneous equilibrium. Yes, equilibriums in a system having more than one phase or different phases that can be found in the equilibrium is known as the equilibrium, heterogeneous equilibrium. And yes, what is this? In homogeneous equilibrium, including all reactants and products in the Kc expression, and heterogeneous equilibrium. Okay.
Oh my gosh. Oh my god. This was so cool. Wow. You can figure it out. Oh my
Okay, I got it.
Wow, 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 wow.
Now next, after this, yeah, first of all, let's go through this. Equilibrium constant in a gaseous system. Yeah, that's fine. But yes, let's try doing that too. Suppose I have H2 gaseous reacting with I2 gaseous to give us 2Hi. Now what is this? Hydrogen reacting with iodine molecule to get 2 moles of hydrogen iodide, that is in gaseous state too. And by getting the Kp in equilibrium state is basically having this in the form of this one. So Kp is equal to pH2 into, sorry, 2 pH here raised to 2 divided by pH2 multiplied by Pi2. Okay, got it. Okay, we got it. Where P is the partial pressure of Kp. Yeah, okay. Where Kp is the equilibrium constant in terms of in terms of partial pressure of the system. What? Okay, partial pressure of the system. Alright. Derive the relation between Kp and Kc. Suppose we have a relation here. A B B gives C. Taking a general reaction. Taking a general reaction here. That's how we are getting this. Okay, reaction. Now, what you can write here. Okay, might have to practice this 2 times. Then we'll move on directly to the, you know what I'm saying. I think we can complete this as fast as possible. Chemical equilibrium. It's gonna take some amount of time, but yes, we can. Taking a general reaction. Let's go. Kp Pc raised to C Pd raised to D. Oh my god, not this way. Kp is equal to Pc raised to C Pd raised to D divided by Pa raised to A Pb raised to b. And by doing this, we get the ideal. Let's put the ideal gas equation. PV is equal to nRT. Okay. Yo. Yep. Finally, scale. Scale tends to fall. It keeps falling. Again and again and again. My eyes. Don't I come back? Stuff fine. But this one is not. Okay, let's extend this and then we will be coming in. Okay,
Okay, so this is the school.
and by we.
I know, I did that 2 times. Okay.
Still a bit
The
confused.
French are crazy right now. I know. The French are crazy right now. Did I say that? Or is it Latin?
We're not gonna give up, guys.
Not that I have so much French language, because it's a really weak language, and people like me trying to speak this.
Okay, what is this? Okay, just wait a minute, guys. Oh, there are so many of these knots. So just come and finally can wear these nicely. It's not gonna stress this out, right? Yeah. Now B is equal to N by V RT. Is N by V a concentration? It says gas. CRT. What is it? Okay.
So the ones that I really like, okay, my top, like my most favorite.
Oh, N by V is a concentration of a gas.
Not that colorful.
So N by V, concentration of gas. Yes, it is mole per volume. We got it. So let's say this is a gas here and this is RT. Then taking P here, P by RT.
I really like this one.
Okay, I have small doubt here. What's going on? What? Mm, 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 mm. KP is equal to CRT raised to C into DRT raised to D ART raised to A B raised B RT raised to B. What is this, dude? Then how did we take KC? Okay, huh? What? should be KP here.
We're starting off with our second. Oh my god.
It just confused me. The derivation is very sensible. Just the way I wrote it makes it nonsense. That's what is going on here. KP is equal to C C RT raised to C
I don't know why, but they're just so
D
I just wanna
D RT raised to D divided by A raised to A RT raised to A B raised to B RT raised to B. This is B. Yep, this is B. KP is equal to wait a minute. How many videos did I upload overall?
so cute. Wow.
How many videos did I overall upload, guys?
This one's like pink and yellow. So nice. I love the grading so much. I don't know.
84 videos.
Did I see this in the box?
When was my channel created then?
Yeah,
I joined
John, right? Yeah,
29th August
yeah,
2025.
yeah. This one's my third favorite.
Let's think about
Wow,
this.
we're starting off
So
really
you're saying I'm not gonna Okay.
ugly. These two are siblings. These two are sisters. They're the most.
Let's go back. Mm-hmm. Okay. Never mind. Going pretty great. And yes. 1 minute, guys. We know that 29th August is there. 29th. Oh, my channel is gonna be 3 months old. Before that, are we capable of literally having over hundreds of videos? Can we do that? Yes, we shall do it. So, what I'm gonna do is 2 videos per day. How's gonna be that? 8414. Not close. Oh, that's not close. 16. I see. So, could be sometimes doing 2 streams, huh? I got it. This is gonna be 86. Well, there will be 86 overall. Still today. So I just need to do only 14 more. 23rd, 24th, 25th, 26th, 27th, 28th, and 29th. We have enough days for that. I feel like we'll do full 100 videos when once our channel is gonna be like 3 months old. We're gonna do that. Don't worry. We're not gonna give up. Okay, let's not waste time. KP PA A P B C P D D C D P A P B B. No, KP. Okay, now P is V is equal to NRT. That means that P is equal to N by VRT. So P is equal to the concentration here of gas raised to RT. So no, not raised to RT, multiplied by RT. So Kp is equal to the C gas raised to C, and then we got D raised to D with RT C plus D divided by, this is A raised to A, B raised to B, RT A plus B. Kp is equal to Kc in dot RT C plus D. I skipped some steps because I want to do it a bit faster. Then we know that C plus D minus A plus B is gonna be delta Ng. So Kp is equal to Kc dot RT raised to delta ng. Let's go. We did it. Now next is applications of equilibrium constant. Okay, we're doing it, guys. How many applications? Calculation of equilibrium concentration. Alright, got it. Are we gonna use some kind of okay, we're getting closer though. I can see through this thingy. First we need to apply Le Chatelier's here. That is very important. The factors affecting the equilibrium. Okay, then alright, not gonna forget that. Standard Gibbs free energy with Kc. Yes, got it. We are close. So two concepts, very major concepts. Applications of what does it say? Applications of equilibrium constant, and another one. Can we do this under an hour? Because I want to complete my full chemical equilibria from here itself. Because how long lengthy is ionic equilibria? I feel like it's very big, but then like we can kind of complete it. I have that belief. We can do it, guys. I mean, I have a strong belief we can do it. Ionic equilibria has some small concepts to go with, and it's gonna take some time. That's what I know for sure. Ionic equilibria will take some time because it's a bit lengthy and it has very concepts and very much a lot of concepts in it. But still, I know I can do it. Okay. Let's continue. Predicting the extent of a reaction. Okay. To predict the extent of a reaction. Extent of a react. Let's continue. I don't like when this stucks. Okay. Calculation of equilibrium. Of equilibrium constant. Concentration. Let's learn the applications now. Wait a minute. Yes, here we go. Okay, so the application of equilibrium concentration. To find the extent of a reaction, to predict the extent of the reaction, we can use the equilibrium concentration. If it is like, having 10 Kc being greater than 10 raised to 3, then this shows that the products will predominate over the reactants. Will predominate over the reactants. 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 Then, if Kc is less than this, or what I can say is it is less than 10 raised to minus 3, then the reactants will predominate over products. Yes, it does. Oh, yep. Application of equilibrium constant. Predict the extent of a reaction. How are we going to do that? In order to understand of how we are going to predict the extent of reaction, Kc, if it is greater than 10 raised to 3, the products will predominate over the reactants. And if the Kc is less than 10 raised to minus 3, then it shows that the reactants will predominate over the products. Okay, and if Kc is between 10 raised to minus 3 and 10 raised to 3, then it shows that these reactants and products that is having a appreciable concentration, both of them. If QC is greater than, okay, reaction coefficient, it's a constant, or it's like a reaction constant where we can actually has the same formula to that of equilibrium constant, but then it can be found at any time of a reaction. Well, whereas equilibrium constant can only be found at when a reaction is attaining an equilibrium state. Okay. If QC is greater than KC, backward reaction is basically taking place. We get to see that a QC is getting much and much bigger here, and if QC is less than KC, we get to know that KC has more reactants concentration. So here the reactants will get converted into products. So forward reaction. And if QC is equal to KC, then it shows that it is in equilibrium state. The reaction is in equilibrium. Alright, we did this. Let's go. Let's just go through this last time. Predict the extent of a reaction. Yup, okay. Product will predominate. We know we need to do that next time. And then if this is then reactants will predominate here, and this will be the appreciable. But this one here, if this is showing, then this is just a comparison. That if this one has, let's say that this would. What are you doing, dude? That this just says that products are needed more. So forward reaction, but backward reaction. What? There are more products. So to get to an equilibrium. Backward reaction. Yep. Why is it so? QC be more. Products will be more. Reactants will be more. Got it. Oh shoot, I should have made that formula chart for chemistry, this chemistry chapter. Oh shoot, I should have made that one. Here, that's how we're gonna show. Now, factors affecting equilibria. Thank you. Factors affecting equilibria. Okay. It's taking time for YouTube to recognize me, huh? It's fine. Take some time while I'll do my own stuff. Take some time while you recognize me. Come back. This is the moment. Giving up. We hate giving up, guys. What am I saying? Okay, factors affecting equilibrium. You and the system. Now we need to understand Le Chatelier's principle. If we increase the product concentration, this says that the reaction should go backwards because it has to form now, it has to attain equilibrium in nature. But if we add more products, if we decrease the product concentration, then to attain the equilibrium, it will go forward. If we increase the reactant concentration, forward reaction, but decrease it, backward reaction. Got it? Got it? Okay. Should more. Clock stable. Clock stable. Pressure of product is increased. Number of moles of the product is increased. Therefore, it should be backward reaction. Yes. Pressure is increased.
Are you doing ASMR?
Number of moles increased.
Are you doing ASMR?
So,
The ASMR is not good. Where's my phone?
okay. Taking some time to understand the whole thing. Just give me time. Then chemical equilibrium will be finished. Only the conceptual part though, because numericals are still remaining. Then we have ionic equilibria. It's still a bit big though. It's not that small. The first one. Effect of concentration change. Let's say this is U, this is system. Concentration, product concentration is increased. Okay, then yep, I can say that the concentration here is decreased, and it is a backward reaction. Concentration of product here is supposed decreased instead of increased. The concentration of product here is increased. That is forward reaction. If the concentration of reactants is increased, then concentration of reactant is decreased, showing forward reaction. And concentration of reactants this time is decreased. The concentration of here the reactants is increased, and therefore a forward backward reaction takes place. Alright, you're applying Lee Chatelier's experience. Principle. Effect of temperature change. That's the second thing. Aha. Pressure, okay. This is U. Yep, very small, I feel. Chat is loading, something's going on. I see. U, and this is P directly proportional to N. System. Now let's think about this. Okay. If pressure increases, what is this? Pressure increases, the number of moles increases. If pressure decreases, number of moles decreases. By the means of saying that pressure is increased, the number of moles being increased, meaning that it should be a backward reaction. Yes. Still have small doubt here though. So pressure, concentration, temperature, inert gases, and there's another one. What was it? Effect, no, not this. Catalyst. The major ones are the first three: temperature, concentration, and pressure. That's the one. You gotta know that too, okay?
Oh my god, what is
Okay. Gotta flow. Have it flow. Have it flow. Have it flow. Have a flow. Flow, 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 flow.
Did I break it? I don't know. This part kind of looks broken. Did I break it? Oh, I hope so. I didn't. Break it. Because this one's super cute. You can even make it into an ornament. Like you can put a garden rug. Like you can put a garden rug. Super cute. But I'm not gonna make it as an ornament. I'm just gonna display it. Oh, why is it not stapled? Does it have a stand? No. Stand. No stand. It doesn't
Wait a
have
minute.
stand. It doesn't. Why do I not stand? I squished the nose, but you can't really notice it.
Okay, yeah, bye bye. Let's go.
Do I?
Hiba, please, please. Don't do that, girl.
Hiba, please, please. So American.
Stop that. Pressure increased. Number of moles increased. Pressure decreased. Number of moles decreased. Stop, don't do it.
Stop doing it.
Ah, sure. Sorry, pressure decreased, number of moles increased. Pressure increased, number of moles increased. By this, what can I say? Backward reaction. Forward reaction. No, bro, what is this? I cannot understand what's going on in this one. It's a bit confusing here. Oh shoot, this is confusing. Okay, well, increase the temperature system moves the backward reaction with decrease in the temperature. Exothermic, yeah. If it is exothermic, temperature is increased, temperature decreased. Let's think about it. Increased forward temperature. Oh, this is confusing. Hmm. Okay. I see. Got it. Here there are two types here. So exothermic. Exothermic and endothermic. Okay. which one goes forward and which one goes backward. So we know that product has its energy being released by increasing the temperature and decreasing the temperature of it. So is it like a backward reaction? Okay. And this one, temperature decreased, and this one, forward reaction. Wait a minute. Oh shoot. Yep, okay. Okay, so this is the one. Hmm. Hmm. This is a bit confusing. Effect of temperature change. Let's first, you know what, I have an idea. Let's do effect of catalyst first. Then we're gonna do okay. Okay. Increases the rate of and backward reaction. Does not affect the equilibrium. By increasing the rate, it helps in attaining equilibrium. Are we live? Yes, again. Okay. Think I'm connected? Okay. Got stuck further for a minute right there. Let's go. But it increasing the rate. Much faster. The effect of inert gases. Effect of inert gas addiction. No, my guy, kaleidoscope. Some rates. Oh. Show that big ad. Show that big ad. Vibrant. No, what the hell? Ooh. They see me TV. Always keep constant. Okay, volume is kept constant. So what are you trying to exactly mention? That if I do not keep the volume constant. Stop tampering with my cam. It always gets stuck. If this gets stuck, you're gonna get beat. Okay, never mind.
Okay, never mind.
I'm studying.
I'm studying. I'm so cute. American. I'm such an American. My accent is so good. Oh my god, I'm not an Indian. I'm such an American. Hello?
Okay, just close. Let's search this up. If volume is not get constant, not kept constant, or we can say a system is isochoric, but I don't want to say that because let's just go clear. I don't want to go thermodynamics concept here. And we add in inert gas like argon. Does that affect the equilibrium? Okay. Actually, this is easy. No, I don't think so. It's correct. It's correct. Finally, chemical equilibrium is all finished. I'm happy. Next is ionic equilibrium, very conceptual part. Half of the chapter, conceptual part, is done. Half of the chapter. Next half is ionic equilibrium, very important to learn. We're gonna learn that now. Let's see how far we can do it. No, I recommend higher. Did recommend. Let's go. Temperature. Let's go through this, okay? Factors affecting equilibrium. Now it looks fine when I practice it. So cases to it, and then it just shows that the products will predominate over the reactants, and if case less than 10 raised to minus 3. 10 raised to minus 3. Wait a minute. You gotta do this. So yeah, I'm just thinking about what is going on. So yeah, appreciable concentration between those. If there, okay, you know what? Let me just read it out loud. What I'm actually like remembering, not saying it out loud. Sorry. So if the constant equilibrium constant affects the extent of a reaction, I was going through this one. Now the second one is the reaction coefficient. The reaction coefficient here is actually also one of the reasons showing the direction of the reaction. If the coefficient reaction is greater than the equilibrium concentration, reaction coefficient. So yeah, oh, okay. If you're having it greater than the equilibrium concentration, or the equilibrium constant, my bad, then we have products more. So that is backward reaction. And if it is smaller, then this will be a forward reaction. If they are equal, then it is equilibrium. It is at equilibrium. Then calculation of equilibrium concentration. Nice. I'm just revising so that I don't forget anything. Yeah, concentration of product has increased, then concentration of product will be decreased in the system, and therefore there will be a concentration of product is decreased. Backward reaction. I was lagging a bit. My bad. I was lagging in real life. My bad. So the concentration of the product, if it is decreased, then the concentration of product is increased, and therefore this is a forward reaction. Early in the morning. Okay. Okay, never mind. What am I doing? Concentration of product, concentration of reactant is increased, concentration of reactant is decreased. Concentration of product reactant is decreased, and concentration of reactant is increased, and therefore the concentration of reactant is mean increased backward reaction. Oh shoot, bro, why do I get confused at some certain moments? Oh shoot. Ah, man, when I'm revising it, I'm getting confused. Why? Product, okay, pressure has increased, number of moles has increased, and since number of moles is getting decreased, it is showing that since the number of moles are decreased, it is a backward reaction. Please. Why am I getting confused? Oh shoot, I'm getting confused. I am getting confused. Oh, if the number of moles are less. Oh, that is there too. There's no change of effect. Delta NG being increased. Delta NG being increased.
हिबा चलो खाने हिशाम हिशाम
Hmm.
आप बेटे खाने बेटे पौधे में देखा हिबा मम्मी बुला रही हिशाम आ जाओ बेटे पौधे में देखा दिलना है सभी
Okay. Okay, we got to know this one line. Okay, wait a minute. Okay, never mind. Ah. Okay. Okay, Casey. Oh, sorry, my bad. I should have said this. Effects. Casey isn't affected by. Okay. Casey is directly proportional to temperature. Oh, this one is interesting. Yo. Oh shoot. Oh. Oh man. Okay. Let's go. We been tough now. Ionic equilibrium. Let's start. Okay. Arrhenius concept. Acid spaces and salts. Bronsted Lowry concept and Lewis concept. Okay. Mhm. Oh no! Oh my god! If you don't know, I'm just going through his video while I'm studying. That's weird. Wait a minute. Okay, so ionic equilibrium. Lukashnik Kumar. Exothermic, endothermic. Exothermic here, endothermic here. This ionic equilibrium. Equilibrium involving ions in aqueous solution. Okay. that involves ions. Ions in aqueous solution. Easy. Okay, my bad. It's easy. So we have many concepts here. Arrhenius concept. Lewis concept and Bronsted concept. Or what is it known? I don't want to say only Bronsted. Lowry concept.
मैंने सुबह स्कूल नहीं जाती
ये से बात खत्म चले जा खामोश
नहीं जाती
जा को क्यों भी ये वीक को तुम 27 को थर्सडे हॉलीडे छता
क्यों
ट्रिप को जा रहे हो कोई ट्रिप तुझे हॉलीडे से खाना
और
खाना खाना
अब मन जा नहीं हो रहा संभाल ले आपको तुरंत डाल रखो
क्या हुआ इससे हाथ को?
दाग लगे
दाग कैसा?
जल्दी जल्दी खाना
और
तुम ना मालूम मैं नहीं खाती
मान अब बाहर हूँ मैं, अब बात तो
थी वो
ठीक है, ऐसा कर गो ने
क्यों बोला
It's fine, we'll go.
क्यों
I'll come back.
हाय जल्दी